Okay, I'm going to create this C cross section. This is really simple because, again, it's a linear static analysis, so you know everything. I'm going quite quickly. New model. You can start with blank or grid only, you know. Then I'm going to modify the grid. Okay, we need also the length of the beam. And the value of the force, that is 1 kilonewton. Yeah. Okay, again, first of all, material. I must switch off the light, maybe it's better. Where is the light? I don't know. Okay, Italy, this is not really important because it's a linear elastic analysis, so the important thing is the Young modulus, that is always this one, 210 gigapascal. And Poisson, that is 0.3, that give us the shear modulus with this relationship. Again, the yielding and stress tensile is not important now because everything is linear. So the new thing with respect to the last time is how to define the AC cross section. I'm going not to import new property, but to add new property. You can select this C channel or a call format one. I'm going to select this call format. You can see that we have to insert manually the dimension. So we have the height, the width, the thickness, radius. I can put 0, I think, in SAP. And the depth. Pay attention to select here the materials. Maybe in SAP, if you put 0 here, that means no lippet. Maybe gives you an error. So you have to put the same value as the thickness. Some programs doesn't accept the value 0 on the radius. Sometimes you have to put a radius that it must be equal or greater than the thickness. In SAP you can put also 0. It's 0, but I think SAP give us an error if I put 0. No, okay, it's 0. Because some software doesn't accept the 0 on the lippet. You can see that the properties are not perfectly equal to the mine, but the error is greater than this difference in 2% of the properties, so I don't go to modify. But as you know, you can modify the property from the section modifier. The only thing that I'm going to modify is the shear area, that I don't want to consider the shear deformation. Let's return to the properties. You can see that here we don't have any information about the warping constant. So this is the first thing that can help you to understand that this beam is not able to catch the right rotation and displacement of a monosymmetrical cross-section. So we have also a very strange thing that say the shear center eccentricity is 0, but because in SAP is not calculated this term. So as you know, in the matrix of the beam element 6 by 6 degree of freedom in the 12 by 12 matrix, you don't have anything that depends on the inertia, warping inertia, and on the shear center. So this is why you don't have these properties here. In SAP, you can also design and implement an external cross-section from AutoCAD, for example, with this section designer. Here you can import from the XF, that means you can create a cross-section in SAP and import inside in AutoCAD, for example, in another file, in another software, and you can import into SAP. Another option from SAP is the general cross-section. This cross-section, you don't have a design, but you can insert directly the properties. So in this case, we can create a general cross-section and insert the cross-sectional area, the second moment of area, and so on. But again, you can see here that you don't have anything about the warping inertia, warping constant. Okay, I'm going to use the C section that I have created. I can show you again, 175, 2, 0, and 0. Quanto è? Is 26, but it's strange because the real value is 5.3. Yeah, this one. The height of the cross section, and the depth is 75. The thickness is 2 millimeters, and the other terms, radius and lip, are 0. I'm going to create the grid. Yeah. Yeah. Some for the shear center depends on the SAP version, because also your colleague have some value on the shear center, but it's not important because in the matrix is not considered the shear center. So you can read also 100, 5, 20, but you don't have any. You can put here the value that you want, but you don't have anything that give you different results. The result remain always the same. Okay, I'm going to create the grid. modify the existing one. I just put in the x direction the length of the beam, so from 0 to 1250 millimeter, and another point in zeta direction to have a square or a rectangular grid. So if you go in the x zeta plane, you have this kind of square grid, or rectangular grid, of course. But we are going to use only this axis. We can draw the beam. This time is a beam element. So straight frame, continuous, and the cross section that is the C section. From 0 to the length of the beam, that is this point. This is our beam. We can see in 3D. This is our C section. I can rotate. I'm going to divide this cross section into different elements, but as you know from the last time, the results is quite independent for this case on the mesh. You can divide the beams by using edit lines. In the edit menu, you have edit lines. You can see that you can divide frames. You can do everything you want. I can put, I don't know, 10. Now we have 10 beam elements. Now we have to apply the external restraint. Again, joint restraint. Everything fixed. In the 0, I put the restraint in the 0 position. So in the initial point of the beam. Last thing is to create the load. So I have to create the load pattern. I created a load that is force. Type is a live load. It's not important, the type. The important thing is the 0 here, because I don't want the self-weight in the analysis. So I have to put 0 here, because if you put 1, the self-weight is considered automatically in the analysis. We have to create the load. So again, joint loads and forces. You can put forces or displacements. Pay attention to select the right load pattern, that is force, the one that I have created before. The coordinate system is global, not local. Pay attention also on this parameter. Because global, I want to refer to the global system, that is this one. And I want to put vertical forces in the zeta direction. Of 1 kilonewton. So 1000 Newton. Okay, of course on the other end. Okay, we can run the linear static analysis. We can remove from the load cases, define load cases, add new one, linear static, from the menu here, static and linear, so no non-linear effects, only linear effects. And of course we have to add the load pattern force in this menu. A lot of you did the exercise of the last time, so I think you are able to perform this linear static analysis. Run analysis, and we can see, of course, we have to give a name to our file, exercise 2. Okay, from the theory, the displacement of this C cross-section is 16.6 and the rotation is 14.21 degree. But you can see from the SAP that the displacement is 3.59. That is the one that I calculated by using the elastic theory of the flexural theory. You can imagine that this is a very, very great mistake because from the practical point of view, you have to verify also the displacement of your beam, not only the stresses. So if you are going to calculate this kind of displacement, you can say, okay, my beam is verified, okay. Then when you are in the practical experimental test from the practical for the collaudo, from the verification of your structures, someone put a load here and found a displacement that is 5 times greater and say, wait a minute, your structure is not safety. There is no way with SAP to obtain this kind of displacement. One trick can be to modify the torsional constant and to apply an additional torsional moment equal to this force multiplied by the shear center eccentricity. But this trick works only for cantilever beam. If you have a double supported beam, then the problem is the same and you have no way to resolve the problem with SAP. In a double supported beam, if you perform an analysis of this kind of beam, From SAP you will obtain always this kind of displacement. But again here you have to add the rotation plus the eccentricity multiplied by the eccentricity between the shear center and the centroid multiplied by the rotation in the middle. And again you will obtain a very different value. This displacement is right, is the true only for one case, that is this one. The load applied on the shear center. Because in this case we have no rotation of the cross section, we have no torsional moment. So in this case this is the truth, but only in this case. Now I'm going to show you a software with 7 degrees of freedom. I didn't say you to download it before because it's a quite long procedure. You have to send an email. It's called Constill. You can obtain also for this software the free license for academic courses. It's an Hungarian software, and in this software you can perform analysis only with the 7 degrees of freedom beam. I'm going to show you the same example by using Constill. Again, here you have to define the material, the cross section, like in SAP, is practically the same. I'm going to define the new material. Again, pay attention on the elastic modulus, Poisson ratio. I put here 0 to not consider the self-weight in the analysis. Cross-section definition, the C cross-section. Here you can see the cross-section. I'm going to call it for example, in Constill you cannot define the radius, and here the lipped must have a value that is equal to the thickness. I cannot put 0 here. From the Constill properties menu, you can see a very important thing that are the torsional properties. You can see the shear center eccentricity that is equal to this one, more or less. And you can see warping and torsional constant. If you want to calculate these properties, you can use the Eurocode 313. Especially the annex. I don't remember if it's the annex C or J. You can create the basic concept of this annex is to discretize your cross section by different points. Point 1, point 2, point 3, point 4. By applying this annex, you can calculate the properties, and especially the shear center eccentricity, the torsional, and the warping constant. I'm going to use the steel material that I have created. Then I'm going to create the beam. This is the graphical view of Consteel. Again, here I have to create the fixed support external. Then I will upload this video on internet. You can see step by step. And the external loads. 1 kilonewton. No, not axial, sorry. When you use Consteel, pay attention on the unities because are kilonewton, sometimes are meters, sometimes are millimeters. And there is no way, I think, I didn't find a way to modify the unities. So pay attention every time when you use it. So you can see that I applied the load on the centroid of the cross section. I can perform an analysis. Here you have some definition of type of analysis: first order, second order, buckling, vibrational analysis, that means the modal analysis, elastic calculation or elastoplastic calculation, and so on. I'm going to put more elements inside my beam, number of finite elements, like 20. Okay, I'm going to perform the linear static analysis. We can check the deformation. This time is more or less equal to the theoretical one, that is 16.3. The little difference is due to different definition of the torsional constant that is in Consteel is quite different from the one obtained by the annex. I don't know how they defined the cross section, but if you put the same value of the torsional properties here, you will obtain 16.3. And you can see also the rotation, that is quite, it was 14.2, here is 13.8. Look at the deformation of the beam. You can see that we have a great torsion, so it's not possible to, it's not negligible, this kind of torsion. If I move the load from the centroid to the shear center, I expect that the behavior is pure flexural. So I expect to obtain the same results give me by SAP. You can see now the displacement is perfect, is exactly the one give me by SAP and the theoretical one, and the behavior is pure flexural, so we have no torsion in this case. Do you have questions? One second.